gas so that we smell it, because otherwise it wouldn't have a smell. So that the smell of gas is not the smell of gas, of propane. It's an additive.
Mercaptan?
Yeah, it's mercaptan.
The sulfur-like smell?
So our detection threshold, that is the level at which we can detect it, is 0.2 parts per billion. Okay, there's no machine that can really do that effectively. No gas chromatograph, nothing. Now, to give you another sense of making this, again, really tangible, we're working with an odorant in our lab called estratetraenol that our participants can detect when we have it mixed at 10 to the negative 12 molar in the liquid phase. To give you a real sense of that, we did the math. If you would take 2 Olympic-sized swimming pools and you would pipette 1 ml, 1 drop into one pool versus the other, you could smell the difference between the pools.
Incredible.
That's the detection threshold that you have with your nose. People have an utterly amazing nose, okay? So that's just in terms of its detection abilities, which are just, remarkable, really up there in the mammalian world. We're not a bad mammal at olfaction. And beyond that, we can improve, okay? And the example you're talking about actually started off as a lab bet. Okay, we were having a lab picnic. So I guess I should here fill in because I'm your guest from the Weizmann Institute of Science in Israel. But before going back to my home in Israel, I was a faculty at UC Berkeley in the Helen Wills Neuroscience Institute. And this study was done during that time. And we were on a lab picnic, and we were having indeed one of these sort of lab discussions, arguments on what humans can and can't do with their sense of smell. And I said that humans could truly even track odor like a dog, and people there said, no way. And we ran this quick experiment, which I have video of, but I don't think we'll show it here. But I actually have original, the picnic video, we have it. And a graduate student by the name of Christina Zolano, a brilliant graduate student at that time, she's now a professor at Northwestern. And she's really leading the field of olfaction imaging today. But she was the volunteer, and we dragged a chocolate bar across the grass and blindfolded her and checked if she could track the track we made with the chocolate, which she did very effectively, right? And
did you place her at the starting point of the line? Or
I think we did. I don't exactly remember what we did on that sort of picnic tryout. But, I assume she never practiced that in her life before, right? And yet, she did it really, really well. And then this went on as a lab bet in a way that I said to my students, okay, we have to make this into an experiment, put it in an experimental setting and quantify what's going on. And they all said that it would be uninteresting. That was the bet. And I told them it would be in Nature, which is a bet I won in this case.
Right. Nature, of course, being one of the 3 apex journals. Science
so it was Nature Neuroscience, to be fair. But so then we turned it into an experiment. And what the experiment is that we brought in participants, naive participants, not graduate students from our lab, completely deprived them of any other sensory input. So we blocked their eyes, we blocked their ears, we blocked everything. They were wearing heavy gloves. They couldn't sense anything. And we generated a consistent odor path in the grass, which is what you saw. We did that by burying twine under the grass, and odor-impregnated twine. So that way we could generate a consistent odor trail every time.
Was it at the base of the grass or in the dirt itself?
It was buried. It was buried under the grass.
Really?
Yeah. Yeah.
Wow. And I did not know that.
It was buried under the grass. And we conducted aerial photography. And participants also had this sensor pack that they were wearing, where we measured nasal airflow in each nostril in real time. And we also used something called RTK GPS, which is a way to lay a radio frequency grid over the GPS grid so that you have millimeter resolution in space, basically. It's used by surveyors mostly, so that we could track behavior. And we found a few things doing this. One is that people could just do this right off the bat. The second thing we found that is when we trained them up, then within average of 4 days, the rate limiting factor became the speed at which they could crawl. So as fast as you could crawl, you could send track. Of course, you can't crawl as fast as a dog can run, but as fast as you can crawl, you can send track. And then to sort of add what made it really interesting from a systems neuroscience perspective is that we asked whether having two nostrils contributes to this. So we constructed a nasal prosthesis, if you will, that had two versions. One is that it combined both nostrils into one big nostril, centered, and the other is that it maintained two separated nostrils. And we compared performance under these two conditions, and people performed better with two nostrils over one centralized nostril, although the flow remained the same. So you're taking advantage of the information that comes from your two totally separate nostrils. By the way, the system I described before of your epithelium and bulb and connection to cortex, you have two of those, right? It's a completely unilateral, well, almost completely unilateral system. There are some very small exceptions to that, but
so a representation on both sides of the brain, much in the same way we have two eyes. We're not a cyclops. We can gain depth perception information. We can perceive motion better as a consequence, and a number of a depth, especially stereopsis.
And we can locate sound because of the difference between our ears and how the head blocks them between. And
amazing. Another question about the mechanics and strategies that you observed, because I think there's information about the system, the brain, as a consequence. Were you in a position to measure sniffing frequency? And the specific question I have is, were people doing something along the lines of a quick sniffing or like a long drawl inhale?
We didn't. So yes, we were measuring sniffing and recording it, and we have all the data. There was nothing very remarkable in that data in that study, although it may reflect that we didn't analyze it carefully enough as well. I mean, it wasn't a major component of our analysis, although we did look at it to some extent. Again, you're asking me about a paper from quite a few years ago, so I may be forgetting parts of it as well. But
I'm sure if it was a major component of it, it would have risen to the top.
It definitely wasn't a major finding of the sniffing behavior in the paper. Although again, sniffing behavior is a huge portion of our life in lab, and it's taking us to places, and it's reemerging now in our work. We're doing tons of sniffing work. I can share with you something that I think will interest your listeners and viewers as well, and we think is really one of the most overlooked things in neuroscience. I'll invite you to do the following experiment. So occlude one nostril by pressing on it from the side and sniff in, and then occlude the other and sniff in. Do you sense a difference in flow?
Yes.
Okay. Do you know why that is?
No, and it was the next question on my list.
Then don't feel badly about not knowing why that is. Most people don't. But that is a reflection of something referred to as the nasal cycle. So in fact, if you were to do that repeatedly, you would find that your high flow nostril and low flow nostril alternate every 2.5 hours on average.
In an absolute way, or is it kind of like a sine wave, like gradual shift to the one and then gradual shift back?
It can vary. It can vary, and we don't yet know the rules, all the rules. But you have this constant shift from side to side. The shift becomes incredibly pronounced in sleep. So we can measure the power of the difference. And in sleep, you have this phase shift of power. You have a huge, like one closes and one opens totally. And it turns out that this is linked to balance in the autonomic nervous system. So as you and your listeners know, we have an autonomic nervous system that has a sympathetic and parasympathetic component to it, and they're in balance or imbalance in many diseases, for example. And this interplay between the sympathetic and parasympathetic nervous system drives the switch from left to right nostril.
Just to remind people, sympathetic nervous system has nothing to do with sympathy, has everything to do with generating patterns of alertness. It's sometimes called the fight or flight system, but any pattern of arousal, positive or negative, and then it's balanced in coordinated way, or at least in parallel with the parasympathetic nervous system, which is sometimes called the rest and digest system, but is associated with all sorts of things, the sexual arousal response, and a number of other aspects of our physiology. So think of it like a seesaw of alertness and calm. Yeah.
Perfect. So now imagine, right? Imagine you would walk around living your life, right? Half of the time with one eye closed like this, and the other half with one eye closed like this. And you had this eye cycle, right? And that was linked to autonomic arousal. I assure you, you would go to PubMed, there would be 5 million papers on the eye cycle, right? And the eye cycle in every disease you can name and what it denotes and what it tells us and what we can do with it. You have exactly this marker. You're walking around with a marker on balance in your autonomic nervous system, and we do nothing with it. So we're in fact now doing a lot with it. Okay, so we built a wearable device that is pasted to your body and measures airflow in each nostril separately and logs it for 24 hours. And we're collecting these 24-hour recordings. We're calling it the nasal halter. So we measure with the nasal halter, and we're finding it as a disease marker. I can give you a nasal halter measurement as an adult, and I can say, this is work by Timna Soroka, a graduate student in our lab now. We can tell the difference between ADHD and non-ADHD adults. And we can tell just from the recording, we can tell if the adults are on Ritalin or not. So I can measure your nasal airflow and say if you are or are not with ADHD and if you are or are not on Ritalin.
Incredible. I have a couple of questions about this. Is it the case that airflow through one nostril is reflective of a sympathetic nervous system dominance versus parasympathetic? Or is it simply the case that this alternating left-right nostril periodicity, which you said I think is on the order of about every 2 hours?
2.5.
2.5. It switches to maximal on one side versus the other. Is that simply reflective of an overall balancing? Is it the hinge in the seesaw, or is it the tilt of the seesaw?
So I don't have a good answer. I mean, I could give you sort of I could say that to some extent, right nostril more open is more sympathetic, and the left nostril more open is more parasympathetic. But that wouldn't be very correct. I mean,
I'm sure that the yogis are going to be all over this,
so
right? Because I get this.
to,
my lab does do some stuff on breathing, and the yogis are always saying, okay, because there's this thing, I don't do yoga anymore, not for any particular reason, but where they'll have you breathe through one nostril or the other. And I've probably been asked this question on social media 10,000 times.
Okay, wait. I'm going to become public enemy number one of the yogis right now. So listen,
they'll come at you with yoga mats, which are not very dangerous.
We really, so since we're so interested in this mechanism, one of the things we'd really like to know how to do is to gain control of it somehow. And there's this world out there of yoga who claims to have control over this. So we said, okay, let's bring like really serious yoga practitioners and see if they can shift their nasal cycle from left to right by will alone, right? Not by manipulating themselves somehow. And if yes, we'll learn from them how they do this, and then we might, use this to cure ADHD or whatnot, right? So we posted like on all the lists of like the yoga teachers and had this parade of yoga teachers walking into our lab. This was one of the strangest
experiments. A lot of sandalwood odors and bare feet.
White clothing and so on. And so we studied, we studied 14 yoga teachers. All 14 by the conditions of enlistment for this came in saying that they can control shifting from left to right nostril
without plugging a nostril with their finger.
By the power of thought alone. And you know how many of 14 succeeded? 0, including one. The most extreme one was we had this guy who and we're recording. And we know how to record this really well, right? And he's sitting there saying, "Yeah, I'm switching now, and it's switching." And you're looking at the monitor, and no, it's not switching. And so no yoga teacher that we found could willfully switch between left and right nostril flow.
And yet they are convinced that they are, and I have to imagine they're not trying to. There's no incentive for them to lie, right?
Yeah, no. Even the opposite. I mean, this puts them in an awkward position once. Yeah, I don't know what the deal is, but none of them can do it.
given that the alternating flow through one or the other nostril is reflective of the autonomic nervous system, has this 2.5-hour periodicity, if I suddenly enter a bout of stress, for instance, does it switch? Because that's reflective of the autonomic nervous system.
Yes.
And the reason I'm asking this question is not because I think that's necessarily important as it relates to stress, but I'm trying to understand the direction of causality. In other words, is the unilateral smelling through, or unilateral nostril smelling periodicity, there when we named it something, I named it the wrong thing, I'm sure, is that driving the shift in the autonomic nervous system, or is it merely reflective of the shift?
So you've very concisely now worded aim 2 of a grant that was probably just rejected, but basically we're trying to answer exactly that question, and we're currently running experiments on that line. So we have one experiment where we're looking, so we're exposing participants to pain. We're using cold water hand exposure. It's a really cool paradigm because there's huge individual differences. We just started this. We built the setup just now, and you have a lot of meat to work with there because there's a lot of individual differences. It's capped at 3 minutes, so for safety reasons, because you have participants putting their hand in 2 degrees Celsius water, but there'll be participants who will pull it out at like 10 seconds, 9 seconds, and then you'll have 3 minutes as well. So there's lots of and already. So now I'm sharing pilot data with you. So to this might, when this ends up being published, it might be the opposite. But so far it seems that the exposure to cold generates a shift in the nasal flow, in nasal balance.
So autonomic arousal can drive the shift potentially. Earlier, you were describing the architecture of these smelling systems, and you mentioned these glomeruli where the olfactory receptors converge in the bulb. And then later you mentioned that the system is unilateral, but with a mirror representation on both sides of the brain. So for those who don't think in terms of neuroanatomy, what Noam was describing is the fact that, of course, there are 2 nostrils and then a bunch of receptors, they converge in these glomeruli, but you have a mirror representation of that on both sides of the brain, and that most of that information is kept on one side of the brain or the other. There isn't a lot of extensive intermixing at the first order of processing. Right. So the question I have is whether or not you believe, I'm not asking for data, first I just want to know what you believe, that this alternating nostril airflow phenomenon has anything to do with preferential processing of olfactory information in terms of right brain, left brain, with the caveat that anytime we hear right brain, left brain, we've covered this in a previous episode. Most of what people hear out there about right brain, left brain, emotionality, logical stuff is completely wrong, doesn't exist, is a total fabrication, and we'd like to abolish that myth. But with that aside, or set aside rather, what are your thoughts on why the information would switch from one side of the brain to the other at all?
Yeah, I don't think that the nasal cycle is an olfaction story. So I don't think that that this was shaped by the olfactory system, nor do I think this has major impact on olfaction. I think the nasal cycle story is a different story about brain function. So we have this sort of pet theory we're calling now the sniffing brain approach, where basically we think that nasal inhalation is timing and driving a lot of aspects and patterns of neural activity and cognitive processing. And this theory is olfaction inspired in its beginning. That is, I mean, if you think of the mammalian brain, right, it's which evolved from olfaction, it's sitting there, and in olfaction, because olfaction depends on sniffing, you have this situation where you have a sniff, you have information, and then flat, nothing, right? And then you have information and then nothing. So information processing is one-to-one linked to nasal inhalation. And we think that this property evolved to be meaningful in brain processing in general, not only of olfactory information, but of any type of information, because the brain evolved in this way that it processes information on inhalation onset. So a study led by Ofer Perl from our lab 2-3 years ago. We looked at something completely non-olfactory. We looked at visuospatial processing, and we compared visuospatial processing on inhalation versus exhalation. And the brain does this completely different on inhalation versus exhalation. You're in that particular task, people performed significantly better on inhalation versus exhalation.
What was the task? Was it an olfactory task?
No, it's a visuospatial task. So this is a task where the specifics of the task were that you see a shape, and you have to determine if it's a shape that can or cannot exist in the real world. So some of them were these like usher shapes, like, where one facet doesn't reach the other facet.
The impossible figure type stuff.
Yeah. But structural shapes, not and so a pure visual spatial task. We intentionally went for a task that is not considered a ventral temporal task, an olfactory cortex task in any way. And people performed much better on inhalation versus exhalation at doing this task.
Was there a both nostrils occluded version where people were forced to mouth breathe?
Yes. And in this particular task, they also did better on mouth inhalation versus mouth exhalation. But the difference wasn't as pronounced as it was with nasal inhalation versus exhalation.
So I'm a big proponent of nasal, not mouth breathing whenever possible.
For sure.
For many health-related reasons. I'm a big fan of the book Jaws, A Hidden Epidemic, written by colleagues of mine at Stanford.
Familiar with it.
Yeah. And this idea that people who mouth breathe experience more colds, more infections of various kinds. It's not good aesthetically or for the dentiture. I never know. The teeth, the gums, it's stuff, folks.
Yeah,
sorry,
stuff.
my dentist is going to come after me. Need to go to the dentist anyway. That nose breathing is great for your health relative to mouth breathing.
So I think it's also good for your cognition, not only for your dental health. I think that nose breathing shapes cognition, and there are other labs who are finding the same. Again, Cristina Zolano is doing work on this line. She had major contributions here, and Johan Lundström is doing work on this line. There's lots of studies suggesting that nasal inhalation is timing cognitive processing and modulating it.
Incredible. Perhaps not surprising, given what you've taught us about the olfactory system. I mean, these two holes in the front of our face, these nostrils, are a pathway to the brain, right? I love to tell people, because I work on the visual system in my lab, that your eyes are two pieces of brain extruded from the cranial vault,
right.
Which they are. They're the retinas anyhow. And then you never look at anyone the same way again. It's okay. But the olfactory sensory neurons are right there at the tops of those caverns that we call nostrils, and they are brain.
Yeah, definitely. It's the only